by the way, about qualitative discussion of symmetries, I forgot to tell you there's a beautiful book about these matters, which I recommend. It's not particularly needed for this course, but just I think it will be a lot of fun to read it. I had a lot of fun reading it. It's the book by Hermann Weyl, the great mathematician, and the book is called Symmetry. So I recommend you, when you have time, to glance through it. Okay, so the statement, we first introduced the notion of functional, a very general notion, and the functional is simply a limit of a usual function of many variables. When the number of variables tends to infinity, in a certain sense, if it has a limit, etc., you get a functional. Much in the same way as you get integral from the finite sums, when the limit, the number of points in the sum tends to infinity. So we said that the functional, the functional associates a number with a function. So we have a trajectory. More concretely, we said that we had a trajectory of a particle or of a light ray just as well. We will be talking today very close, very much insisting on the analogy between light rays and mechanical particles. So we have a trajectory given by some parameterized by time in this case. And we said that the functional is generally just a prescription how to get a real number or a complex number from this thing. And more concretely, we looked at the functional, which is the difference between kinetic and potential energy. It's not the only functional which is interesting. We will see today, well, in a few minutes, you will see other example of meaningful functionals. But what we demonstrated, first of all, that we demonstrated that the functionals can be differentiated. Let me remind you what we said. We said something like that when we have a function of n variable, a convenient definition, I'm repeating it to set up notations, which I hope will not be confusing. We say that let's shift each variable. Delta xi is simply a shift, and we assume that we will be keeping only terms linear in delta xi. And the change, the variation of the function is sum is just this sum, and this is the definition. This should be looked as a definition of what we mean by partial derivative. It is the linear part of general notion of derivative. In many cases, for example, you can similarly define derivatives in some non-commutative spaces and so on. It's very general. It's just the coefficient in front of linear variation of your argument. In this case, it's just delta xi. And analogously, we define the variation of the functional variational derivative by we change x of t, keep up the linear term, and the general definition is that it must be linear in delta x of t dt. If something is unclear, please interrupt me, because it's rather simple and trivial matters, but if you miss it, it will confuse you later with non-trivial matters. It always reminded me, you know, that like you are being introduced to somebody and you don't hear the name and you are shy to ask the name, and that leads only to embarrassment afterwards. So don't hesitate to ask about notations, about anything actually. Anyway, you see that that's the way how to calculate, that's the definition, this linear coefficient in front of linear term. More general class of functionals, which you certainly know, described in any textbook on mechanics, is the functionals of the type when you have the function, called the Lagrange function, which depends on x and x dot, and you integrate it over t, and it is completely straightforward by the same method to derive the equation of motion which follows from here, the Euler-Lagrange equation.
Does the definition of, does the value of delta S depend on the dummy variable t that we choose?
Okay, that's a good point. You see, in this case we vary only we vary only delta x of t, and so it does not depend on t explicitly. It depends on t only through this thing. Just like with the partial derivative, you see that partial derivative, you have one function, you differentiate, which depends, this function does not depend explicitly on these numbers, or on the number k. It depends only on these variables, and we differentiate it. If you can introduce extra variables and try to, sometimes it is useful, but in this case it's not. Okay, now there's another functional which will be very useful for us, and this is a functional which associates when you have a particular curve. Suppose you have a curve in any dimensional space. The natural functional is the length of this curve, because for each curve it associates some number, the length in the Euclidean space. What would be the explicit expression for this? Well, it's a bit. L here is the length. L here is the Lagrange function. They're not related at this point. So, what is this functional? Suppose you have, suppose you have, how would you calculate? You parameterize the curve. For instance, if you have two dimensions, example, x1 is r cosine s, x2 is r sine s. Which geometrical figure it describes? Huh?
Circle.
It's a circle. How we calculate the length, knowing this thing? It's a parametrized circle.
Integrate with respect to ds.
Yes, you are right. Integrate what? That's the only question.
The absolute value of dx.
Yes, that's correct. And you can do it in several ways. You can say that it's absolute value of ds, as you suggested, say from 0 to 1, if you parameterize it in this way. This means just square root ds square over ds. And in principle, you probably know from the calculus another expression which exists in 2 dimensions. Let's suppose we have a curve y of x. It's an example again. And we know that to calculate the length, you have to integrate over x square root of 1 plus dy dx square, because from the simple geometrical construction. And for a circle, for instance, what is y of x?
Square root of the minus.
Exactly. And you notice that in this way it's a little bit more clumsy to write it down, because it gives you an impression that at the point x equals 1 you have a singularity, which you don't have. So while in this parametric representation it's better. There is nothing singular. Now, how these two expressions are related? Let me write it down in 2 dimensions as square root of dx1 ds square. It's a slightly tricky question. It's not a completely trivial question, but it's important for me. So I have this expression for the length, and I have this expression for the length. To make it even more, it's sometimes the choice of letters helps. So let's write it down this way: dx ds square, dy ds square. And they both are supposed to be the same thing. And there's a simple way from one to another. Notice that what you ask yourself, what should I do to squeeze it into this expression? Yes, exactly. So you can do 2 things. Either you can write it down as dx ds, ds, and then you replace integration over ds by the integration over dx. So it's just change of variable. But there's also another way of viewing the same thing, which is to say that this expression is invariant under very important transformation. Namely, if you have this expression doesn't change, this expression, the general expression doesn't change if you replace, it's some interesting symmetry, if you replace x to x of f of s. So let's change the parameter. For instance, when we talk about a circle for which x1 was cosine s, x2 was sine s, imagine that you are doing, you consider a different expression, x1 cosine s square and x2 sine s square. Which figure is this? What is geometrical figure described by this curve?
Also a circle.
It's also a circle because what we both of them the easiest way to see it is to notice that both of them satisfy this equation. So it must be the circle. So the curve, the geometrical curve, is invariant under reparametrization. We actually say that when we write down this expression, it's defined modular change of the parameter s to f of s. Now, this changes us when they are smooth and have good mathematical properties. They are called diffeomorphisms, provided that also they are one-to-one, give one-to-one correspondence. Now we have to. The first comment which we make is that two different parameterizations describe the same curve. Okay, and then if we don't know the expression for the length, what we must require of this expression. What I'm driving at, let me explain you what I'm talking about. I'm trying to figure out the expression for the length on the basis of symmetry, geometry, etc. Let's suppose that we don't know this expression. What kind of terms, what kind of integral it can contain? This expression is uniquely defined. What I'm saying is that this expression is uniquely defined by its symmetries. And what are the symmetries of this expression, of this functional? Let's discuss. One of them we already discussed. Namely, let's check. It has parametric invariance. Let me very briefly show you how it almost. All I'm saying, it's algebraically it's almost trivial, but physically it's very important. So we have dds x of f of s integral over ds. Now we use the chain rule. We get dx df df ds ds. So if this is positive, I shall explain in a second why it is needed. It's simply integral dx df over df. So it's just the same expression, just we renamed the independent variable. Now there is only one small thing here. We have to assume that df ds is bigger than 1, bigger than 0, excuse me. What does it mean geometrically? What do you think? If we have when the parameter evolves, you can visualize the curve being drawn. So what does it mean why it appears that we have this requirement that dfds is positive. So you, for example, you start drawing the circle, and that this process is changing of parameter s. So what happens if the derivative of f of s changes sign? Yes?
You have a negative in front of
The what?
You have a negative in front of the interval.
Yeah, you start backtracking. And that changes the length, obviously. And more rigorously, more mathematically, f of s is a map from, say, one interval to another. And what is unacceptable is to have f of s of this form, because that will not be one-to-one correspondence. You see, when you are here, the given value of f would correspond 1, 2, 3 points on the original in the s variable. There will be 3 values of s corresponding to 1 value of f. So, and to avoid this, we use this diffeomorphism, and then it is called diffeomorphism, or also general coordinate, general transformation of variables. So we have this remarkable thing, and basically this reparametrization symmetry determines the functional. Plus, but you have to add something else. So what is much, there is also much simpler symmetry which is present here. Yes, please.
Rotation.
Yes, rotation and translation. The length, if we want the length, it must be invariant under rotation and translation, and it is. Now, and now you simply say a very simple thing. You're saying, I want the functional with minimal number of derivatives, which has parametric invariance, which has diffeomorphism invariance. That's the synonym. And it has symmetry under rotation and translation. If we, by the way, how would you modify it? It will not be unique if you drop translation and say rotation only symmetry. Then you have many functionals. Give me a simple example of a functional which has parametric invariance, like this one, rotational invariance. I'm building on your question, on your comment, but does not have translation invariance. What can you add to the integrand?
Magnitude of x.
Add
magnitude of x.
At 9?
Magnitude of x.
Yeah, well, you can add x squared, for example, and that's. But translation forbid it. And now we argue the length must be, almost by definition, translation rotation invariant. It must be also parametric invariant, because different parametrization describe the same curve. So the length does not change. Then that's the only functional with minimal. You can add higher derivatives, and sometimes you have to, but we will be talking about this issue many times in this course. In order to describe low energy physics, you need expressions with minimal number of derivatives. And higher derivative terms are just correction. If you allow higher derivatives, you can write down parametrically invariant expression like that, and you can, which will have translation rotation invariance, so it will describe a curve. Guess what it is if you have some next term with higher derivatives. Not the, I don't mean the expression for the term, although it also can be done, but just the geometrical meaning. What could it mean when you have a curve?
You don't have a Euclidean space anymore.
Well, no, I have a Euclidean space. I don't want to go. Well, we will leave the Euclidean space shortly, but at the moment we are there. Yes, please.
Do you mean higher order derivatives or
Yes,
derivatives raised to a higher order?
Both. Actually, they come together. Well, let me tell you, it's one of my many unfair questions. What I'm saying is that the curves in geometry, they have different properties like torsion, and these are just the invariant expressions. When you see, it's basically the curve described by this action is infinitely thin. If it has, if it is a tube instead of an infinitely thin curve, you will get some higher terms which are curvature, torsion, etc. Something which I assume you know from differential geometry course. And if you don't, it doesn't matter. My point will be independent of this. So one interesting thing here is that we determined the functional on the basis of physical requirement. We will do it shortly for mechanics, but let's let us talk a little more about this thing. By the way, before I go further, if I start functional differentiation, if I have stationarity conditions, so the general extremum condition is this. Suppose I will do the differentiation. What will I find from the condition like that? What kind of answer I will get if I write down the equation that variation of L is equal to 0, the extremum condition. It's not a big deal to calculate delta L, but I don't want to do this at this moment. I want you because I want you to foresee the answer. Actually, yeah, go ahead.
Straight line.
It should be a straight line, but okay, good. But tell me what kind of x of s you will find when you solve the equation delta L equal to 0. It's a concrete equation and it can be solved. Let me write down the equation as an exercise. You have this thing. And you write it down as 1 over square root of dx ds square dx ds d delta x over ds, and then you integrate by parts like we did here and get some somewhat clumsy equation. I will probably ask you in the home exercise to finish this. I will ask something more complicated, not that. But in any case, I'm not interested right now in solving this, etc. I'm interested in the answer. And in a complicated problem, you never can solve a complicated problem if you don't know the answer. So you have to foresee the answer, what the answer will be for x over. And you almost did this. It's a straight line, but written in which way? Some example of straight line. Give me an example.
Constant times
It's a,
constant times x.
what?
Just a constant times.
The constant. Yeah. Well, we have if it is a constant, it is if it's just a point located at A. Generally speaking, you might think that something like this will describe a straight line, but it's not the general. And that's true. It is one of the solutions. But you now, after what we discussed, you now should think about most general solution of this equation.
We can turn the S into an F of S.
Exactly. And interestingly enough, when you start solving this equation, you will find the arbitrary function in the solution. As it should be because of diffeomorphism symmetry. By the way, and it will be part of the exercise, I guess. By the way, you probably know another part of physics in which diffeomorphism, invariance, or symmetries like that play fundamental role. Is there anything analogous of which you definitely heard, but some theory in which all coordinates are just could be reparametrized? The theory in which you have, say, n-dimensional thing and you parameterize it. You replace them by function, or perform diffeomorphism in n dimensions or in 4 dimensions. What are the theory invariant under diffeomorphism in 4 dimensions? How about, do you remember about an obscure physicist named Einstein? What do you know about theory of gravity? Okay, I will tell you. The most important part of this theory is that coordinates are that it is invariant under the n-dimensional, 4-dimensional diffeomorphism, and all kind of paradoxes that Einstein first realized the equivalence principle that you can replace acceleration. Going to accelerated frame is the same as including gravitational field, and from there, well, probably I should not be, I'm digressing too much. But I shall now return to what we briefly discussed on the previous lectures, namely propagation of light in the medium. Suppose you have now let's suppose we have a medium with the refraction index n of x, which depends on x in some way. What would be the variational problem? I mean, which functional should be extremized in order to find the propagation of the light ray. Well, first of all, if n is equal to 1, then what functional we should be talking about? The light, I remind you, propagates so that it takes minimal time under the circumstances. So if there is no refraction index, if it's equal to 1, the speed of light is constant, then what? That's a trivial question. Huh?
Straight line.
Straight line, yeah, but which functional we have to minimize to find this straight line? It's of course this one, because this length is equal to, because speed of light is constant, if speed of light is constant, then this functional, this length is proportional to time which take for a particle for the light ray to which the light ray needs to go. Okay, so it's a good starting point for n equals 1. And it's pretty easy to generalize it to the case when the light propagates in the medium in which you have some non-trivial refraction index. So what functional, let's call it t, the time which we need to propagate, what would be the expression for t? I remind you that local speed of light is, if you have refraction, then speed of light is related to this. And
so 1 over C naught times.
yes, sort of. And what's the oscillator? Yeah, right. So t is simply C naught. Let's set it to 1. Speed of light in the vacuum. Time will be n of x of s dx ds ds. And so we will need to extremize these functional in order to find the light trajectory. And what we will see very soon is that there is a lot of relation between this minimization and this apparently totally different expression. So once again, and I don't remember if we have it. I don't think we have it in the exercises, but we will add it. One of the nature exercise is to imagine that you have, let's suppose we have this y and x, two-dimensional medium. As you know, by the way, that it's the dependence on x which is responsible for mirages, because the light doesn't want to go to the places where it's too slow, and as a result we get curve. Now let's suppose that the refraction index depends only on y, but does not depend on x. And in this case, I would like, well, first of all, maybe let me try. That's not so trivial question, but not terribly difficult either. What do you think will be the answer? How the light will propagate if we have the refraction index? I will give you a hint. In this case, the propagation of light is very tightly related to the Snell's law. Why is that? Well, I'm giving you a few hints, but after all, you will have to solve the equations yourself. Imagine that you have layers, and you have n1 here, n2 here, n3 here. In this case, you get typical situation in which the Snell's law is applicable. And what I basically want you to find out that by variation of this functional will give you the corresponding Snell law. Okay, well, that's a minor digression. But now let's you can say, how am I doing with time? I get carried away a little bit with this matters. You can say, okay, all this, why should we be interested in this? It's all, after all, it's equivalent. It's just some funny way for writing the Newton equation. The physics is the Newton equation. And people did say that when variational principles only appeared. Well, the answer to this is that when you find some very unexpected and beautiful representation, it will help you to generalize things, to go to the unknown. So far, we just rediscovered something which was known without it, the Newton equation. Now we will find out the relation between symmetries and conservation laws, which is not so obvious from the Newton equation in complicated cases. And then, actually, when you go beyond classical dynamics, it turns out to be an extremely important quantity. The action and the least action principle is very important. It's basically the Planck constant, which is involved in quantum. When you go to quantum case, is the minimal portion of the action. The action is an important quantity. All right. So let's look at the. Let's keep this in mind. We will be considering these simultaneously, and at the end they turn out to be the same thing. So running somewhat ahead of myself, what we will see is that when particle propagates in a potential, it is mathematically identical to propagation of light with a certain refraction index related to this potential. So, and another thing are the question of symmetries. So let me take one simple example. Let's take many particles, and we have. Let's look at the action when you have some. And something which we started with. And in this case, an integral over dt. In this case, we have obviously we discussed it in details on the first lecture. We have the symmetry. The symmetry under translation. Now let's do the following trick, which is called gauging. Let's make parameters. A are the parameters of this symmetry, of this translation. Let's make translation time dependent. Translation time, of course, the action will not be invariant anymore under time-dependent action. But, so the action will change. Let's calculate the change. This term, by the way, will not change at all. It's for these the symmetries, basically the symmetries for which parameters depend on coordinates, on time, they are called in general gauge symmetries. Digressing a little bit, our world is full of gauge symmetries, as described by the Standard Model and Einstein theory of gravity. They are all invariant under gauge symmetries. Okay, but in our case, we simply have M, sum of xi dot, a dot, dt. Now, this is this is something to be foreseen, that variation of the action when you have a of t should be some expression multiplied by a dot of t dt. This is to be expected. Why? Why it should be expected? We got it by direct varying of this term, but it is not an accident that you get a dot and not a, for example. Why we don't have a in this expression?
Is it because of translational symmetry?
Exactly. The expression should be such that if we set a equal constant, variation disappears, because the action, by the assumption, is invariant under translations. So let's call this something P. And for any symmetry, you cannot get higher derivatives, by the way, because we don't have higher derivatives in our Lagrange function. In general, you can have also higher derivatives. That doesn't bother me at the moment. If you perform rotation, you also find rotate. This is translation, gauge translations. Gauge translations. A variation is gauge rotations I remind you, the rotation, the infinitesimal rotation, you have coordinates x alpha, and let me remind you that we have variation of x alpha must be 0. So it will be the case if infinitesimally, so delta x alpha must be 0. So you need omega alpha beta. These brackets mean it's anti-symmetric. So omega alpha beta is minus omega beta alpha. How many rotations we have in 3 dimensions? Suppose you have 3 dimensions, and you have a anti-symmetric matrix 3 by 3. How many independent, well, you may think geometrically, how many independent rotations you have in 3D?
3.
3, of course, yeah. How many would you have in 4D?
6.
Yeah, why not 4? Why? It seems that at the first glance, if you continue, your answer was right, but suppose that we try to argue like that. We have, in 3 dimensions, we have 3 axes, and we can independently rotate around each of them. In 4 dimensions, we have 4 axes, so it seems that there are only 4 rotations. But that's wrong. That's the wrong argument, and your answer was right. Indeed, if you look at the 4 by 4 matrix, there are 6 independent quantities there, 6 independent angles. How would you explain it geometrically? I'm sure you can easily imagine 4-dimensional space, and that shows how much easier it is to work with algebraic representation of geometric problems. There's some tendency in modern mathematics, which like topology started purely geometrically, but most powerful result was gained in algebraic topology and so on. Anyway, but you have, in this simple case, you have to, don't want to spend too much time on this, you are supposed to think that rotation is a motion in the plane. Alpha beta here, you have coordinate planes 1 2, 1 3, 1 4, 2 3, 3 2 4, and 3 4. And you can rotate independently in any plane. So it's geometry of this is just that it's wrong to think about rotations as rotation around the axis. You must think that rotation is rotation in a plane. In 3 dimensions, what's confusing is that in 3 dimensions it's the same thing. But in any other dimension, the red flag, by the way, can be seen in 2 dimensions. You see, in 2 dimensions, you have only 1 angle, not 2. Okay, so gauge rotation by the same argument will give you something like, let me call it J alpha beta omega alpha beta dot. I forgot the important dot. So far, I didn't make any interesting statement. I just told you that how the action changes under gauge transformation. And here, once again, we say that for constant omega, it should be 0 because the action is invariant. And so here we are. All right. And now let's make, now it is one-line argument, which turns it out in one of the most important statements in modern physics, what is called the Noether theorem. Namely, let's rewrite. Let's start with this. Let's choose, this is the integral from T1 and T2. Let's choose A of T1 equal to A of T2. And then we can integrate by parts and write it down as P dot A of t dt. And now you finish my argument. How to show that from this this quantity P is conserved, that is, its time derivative is 0. It's very simple but slightly subtle argument.
I have a question about
Yeah,
this.
please, sure.
So could you explain why the two lines you wrote on the top are true?
You mean this one?
The delta x alpha,
Ah, this one. And to explain what?
why it's true?
Oh, okay. You see, we define rotations, or in this case, I'm interested in infinitesimal rotation, as the transformation which doesn't change the length. So variation of x alpha is 0. What is rotation? Well, it's basically a definition of rotation. Now I simply say so delta x alpha must be orthogonal. Delta x alpha under rotation must be orthogonal to x alpha itself. And it is achieved if you choose delta x in this form. It's pretty easy. I will not stop on it to show that that's the only possibility. But that's for the infinite. We did this. It's basically at the first lecture I looked at the finite rotation. We introduced orthogonal matrices, which preserve x squared, and this is just the infinitesimal version of it. For our purposes today, we need infinitesimal transformations, not finite. But returning. So what I did here, since it's all quite important and simple, it's simple but a little tricky. Let me do it this way. First step, we just blindly calculate variation of the actions under gauge transformation. We got this formula, If you have some other symmetry, you get analogous formula. For example, some action may have dilatation symmetry, rescaling symmetry. You will get analogous expression. In all cases, you will have some concrete expression here, which will stand in front of omega dot, a dot, or whatever you call corresponding parameter. Okay, now the next step is a of t is in my disposal. I can do whatever I want with it. And I want, for the reason you will see in a moment, to impose the conditions that at1 is equal to at2. Then integrating by part gives me this expression. And now I want to ask you, what conclusion should I make from this? It doesn't require any calculation. It just requires some small thinking about the meaning of this expression. So this is our variation. By the way, it's how would you the trivial? Let me start with a completely trivial question, but maybe it will help. The trivial question is I seem to be contradicting myself, because I was saying it should be variation should contain a dot, not a. But on the next line, a appears here. Why it is not a contradiction? What I needed to do when I came from here to here, I had to use this. It will not be true if there is no this condition, because what I really did, I simply was doing this thing, ddt of PA minus AP dot. I use this identity to go, which is integration by part, to go from here to here. But I want you to make one logical jump from here and conclude. The conclusion should be that if the Newton equations are satisfied, then P dot is equal to 0.
Take A to be a constant.
Yes.
Perform the integral.
What?
You take A to be a constant and then you perform the integral.
Well, if I take, that's right. I can do this, of course, but well, there is a subtlety here which I want you to appreciate. So I will return to the subtlety in a moment. There is the simplest way to proceed here. It's really a very, very simple way to proceed, which is to say that the action is extremal. If it is extremal, it is invariant. If Newton equations are satisfied, delta S should be 0. It doesn't matter how you vary things. It's 0 under any variation, in particular under this variation of A. So so we conclude from here that P dot A is 0 for arbitrary A, and that can be only if P dot is equal to 0. And P dot, so returning to what it tells us about this thing, it tells us here it's trivial. And once again, this will not true. This will be true only as a consequence of the equations of motion. It's not just an identity. It's important to this step is very important. Now let's calculate this thing with rotations as another example. With rotations, it's the real calculational part is just to we have m divided. Let me erase this. Delta xi alpha is omega alpha beta xi beta, and we have delta s being integral sum m x I dot delta xi. So we have integral sum m x xi alpha dot xi beta omega alpha beta dot dot here. So as a result, we conclude that the quantity J is sum or m xi alpha xi beta dot minus vice versa. In 3 dimensions, it's simply the statement that sum m x cross x dot is equal to 0. So this quantity is called angular momentum. So we see that rotational symmetry leads to conservation of angular momentum, while translational symmetry leads to conservation of momentum. And basically all conservation laws, the existence of conserved quantities, is the consequence of symmetry and the least action principle. I will give you, there is one more important thing, which is conservation of energy. It's an interesting case. So it's quite important, actually. See, the key point here is to realize that the action, that the Newton equation or equation of motion means that the action is extremal under these conditions. And that immediately leads you to conservation laws. I also want to stress that for not any equation can be cast in the form of a least action principle. It's a very strong requirement that the equations are symmetric under this. We can now ask the following question. Well, maybe I shall do one more thing, which is conservation of energy. We didn't do conservation of energy here yet. We looked at the conservation of momentum, conservation of angular momentum. Now, conservation of energy. Conservation of energy is related to the time translation invariance. Now, what should I do? A is infinitesimal, but it will be actually easier to deal with finite. What should I do to go along this path? I want now to derive the consequences of this symmetry in the least action principle. So, suggest me how to proceed from here. We see that this action is invariant under these transformations, but what shall I do next? How to calculate? And we already learned that there should be some relation between symmetries and conservation laws. But what I'm supposed to do with any symmetry? I'm supposed to gauge it, right? We gauged symmetries, gauged transformations. What? Yes. So let's consider what happens if I change, if I look at the x twiddle, or simply change x to x of t plus a of t. So time now is transformed in a time-dependent way, or I shall write it down as x of f of t. So I'm now studying how things change under reparametrization. Remember before, when we talked about optics, we had actually parametrically invariant things. Here it's not parametrically invariant. We actually write down it in a very simple way. We see that dx dt it should be replaced by dx ddt of x of f of t, and this is equal to dx df df dt. So far it's very similar to what we have been doing there, but now we have an actually let me use this notation. So we have integral ddt dx df square df dt square. Okay, and we have to integrate it over dt. That's the first part, the first term in the action. The second term in the action is minus v of x of f of t integrated over dt. And what is the last transformation? So it's just change of variables. The last transformation for S2, I will write down as integral over df v of x of f. I introduce new variable f, and here I have 1 divided by f dot of t. Okay, it's just dt df df. Now S1, it's a little tedious at this point, but you will be rewarded for this. Here I also will take the variable f, and I have integral over df. F dot here will be in the numerator, and it will be dx df square. Okay, that's all calculation which have to be done, and now comes the easy part. Namely, notice what is very important is f dot enters differently in kinetic and potential terms, and I now go to infinitesimal, and I see that delta S is actually equal to integral a dot Now this plus, you see we have in the Lagrange function we have a minus, but these two terms, kinetic and potential, transform differently. That's very important. They one transforms with f downstairs. This transforms with f upstairs, which basically actually very easy to understand intuitively. Look, we have the expression dx dt square over dt minus v dt. Let's count the number of dt's. You see, this first term is proportional to 1 over dt. it contains dt square and dt in the numerator. And this term is linear in dt. And that's reflected in this thing, and that's reflected in the fact that now you have the expression, the potential term gives you a different sign than this term. And now the same logic as here. You simply say it is a dot, we integrate by part, and we come to the conclusion that ddt of this expression, which we call energy, is 0. It's the consequence of this thing. Now let's calculate suppose this was the calculation of energy for the Lagrange function mx dot square minus v of x. What if we have the Lagrange function like here? Or let's suppose it is just square root of x dot square dt. Suppose we have this Lagrange function. Can you right now tell me what would you expect? What would you expect from the what kind of energy will be related to this straight line length or something? Maybe it's not very fair but question, but in principle, so suppose you will do all these transformations. We will be discussing it next time, but I just want you to get a taste of it. So suppose I reparametrize time. What will I get here? We sort of did this already. So all we did here, we reparametrized time and we found energy here because of this. What I was telling about the first part of the lecture, about this type of functionals, about how they behave under reparametrization.
It's the same.
They don't change under reparametrization. So what does that mean from the point of view of energy? That's the last question.
Energy is also invariant under.
The what?
The energy function is also invariant under.
Say it again, I don't.
The energy transformation would also, or the energy would also be invariant under this.
Yeah, but you see, we will discuss it in details next time, but the point is that here we got the coefficient in front of a dot. What you will get for this function will be identically 0 because they are parametrically invariant. So the energy will be 0, and that's why the total energy of our universe is 0 actually, because it's described by covariant by parametrically invariant equations. Okay, with all these interesting things we will discuss next time. Let's stop here.